Pastor Joe, please.
Okay, thanks for the introduction and thanks for the invitation to this event. So do I need to connect because the slides is not on yet? Okay. Today I'm going to talk about the DeFi protocol security, the lessons we have learned, and some new developments in this area. My name is Xiaojun Zhou, and I'm a professor at Zhejiang University. And I'm also a CEO of BlockSec. BlockSec is a full stack security providers. And so I'm a co-founder of BlockSec, and I'm a professor at Zhejiang University. My research interest including the DeFi security, blockchain system security. So we develop different tools to detect the vulnerabilities and hacks on the blockchain systems. And we have some work, to improve the performance, scalability, security of the whole blockchain systems. And I'm a professor at a university, so I need to publish papers, otherwise I'll be fired. So I publish papers and I hack and build systems. Okay, so the DeFi protocol security matters. So even in the bear market or the bull market, the losses due to the DeFi hackers are still increasing. And we have a DeFi security incident dashboard inside a BlockSec. So this dashboard includes the security incidents happened each month, right? So this figure shows the security incidents happened in October and September. So from this dashboard, you can still see that a single DeFi security hack can cost like more than 58 million US dollars. So it happened a couple of days, a radiant hack. So why security incidents are prevalent? There are a couple of different reasons. The first reason is the economic incentive. So we already saying that the hackers, they hack the DeFi protocol, not just for fun, not just to show that I'm very good, at a hacking system. They hack the DeFi protocol for profits. So because they can get paid, by hacking the DeFi protocols. The second reason is that we do not have a large number of the security qualified developers. So most of the developers, they are trained to develop the functional protocols, not just secure protocols. And in the DeFi ecosystem, it needs the knowledge from different disciplines, like we need the knowledge from the computer science, from the finance, from the cybersecurity. So we unfortunately we do not have a very good human resource in this area. So even the PonyU has the master program of the blockchain area, but still many of the universities do not provide such talents in the market. So we do not have very good security qualified developers. And DeFi, the protocols in DeFi relying on each other to function well. So one protocol, they may need the information, the data, the price information from other protocols. So you need to consider how other protocols work when operate on your own protocol. So it costs extra attack vectors. Also, the blockchain is an open system, and everyone can interact with this system. So think about a banking system, right? So even if you find a vulnerability inside the banking system, it's hard to hack it because you need to physically access to a system. But on blockchain, you just send a transaction to interact with the protocol, okay? And some other, I will not go detail each by one, but the flash loan and some other aspects also, make the security incidents prevalent in the blockchain system. And we also see some new trends in the DeFi protocol security. So the first one is that unfortunately, some very well-known protocols have been hacked. So for instance, in last year, the Carbon Swap, Curve, and the Balancer were hacked with millions, maybe more than millions US dollars loss. This protocol has been running for a very long time, like the copper swap has been running for 6 years without any security incidents. But last year, the copper swap was hacked. And all these protocols have been audited by a couple of different companies in more than 10 rounds security auditing, but still they have vulnerabilities. They have new attack vectors that were unknown before. Second is that we see some new types of the attack vectors. For instance, the compiler bugs, right? So when we started cybersecurity, our professor says that the compiler may have bug and it will cause the security issues, but we didn't see any real cases for that. But in last year, we see a real case. The compiler bug caused the curve protocol being exploited. That's because there's a bug inside the curve, inside the compiler. It makes the security mechanism enforced by the curve ineffective, so that attackers can hack this protocol. And also there are some incompatibility between different common standards. That's also it's just the the issue I'm talking about is the DeFi composability, because the DeFi protocol need to interact with each other. So if there are some standards they are not compatible with each other, this will cause new issues. Okay. And then the third trend is that we see some older issues have new security impacts. Let me give you one example. It's a precision loss. So precision loss is a very common problem in the program language. So typically we do not treat the precision loss as a vulnerability because it's very hard to exploit that. But combined with some issues in the lending protocol, we call it the uninitialized markets, then the precision loss bug can be escalated to the vulnerabilities and can be hacked by the attackers. Okay, and what's the existing approaches to protect the DeFi protocols? So currently we are mainly focusing on, we call it the pre-launch security. The pre-launch security means that we can perform the security code review. We can use in formal verification, and we can use in the fuzzing testing, to ensure that we try our best to locate the vulnerabilities before the smart contracts are being deployed on the blockchain. So this is the main existing approaches. But what's the issues here? The pre-launch security works in some extent, but not enough, right? That's why we still have DeFi hacks every month since like 2018. Every month we have the DeFi hacks because most of them are using the pre-launch security methods. So we need some new solutions. We also need the post-launch security. The post-launch security means that after the protocol is deployed on the blockchain, we still need to monitor the protocols. If there is any attack transactions to the protocol, can we develop an effective approach to block these hacks? So this is the ideal one. Second is that can we develop a blockchain with some inbound security measures features inside the blockchain? Can we develop a blockchain with the security feature inside the blockchain to prevent these hacks? Okay, so I will talk about each one of them. So before talking about the blocking hacks, so let me summarize the steps of a DeFi hack. So basically, the hackers will prepare the attacker. They will give the gas fee from some like the mixing services, and then they will deploy the smart contracts, and they will launch the attack, and after that, they will earn their profit using some mixing services. Okay. So what's the process of a transaction is confirmed on the blockchain? So basically, a transaction is broadcast to the P2P network, and every node on the network can listen to the pending transactions, and the validators will confirm these transactions. So our idea is, can we detect and block the attack transactions during this time window, the T1 and the T3 time window. So typically it's 12 seconds on Ethereum and 2 or 3 seconds on the BSC network. Okay, so it turns out that we can do that. We can develop a system right? So we can listen to the pending transactions in the Ethereum mempool. So we can have a transaction execution engine to simulate these transactions. And then we use an attack detection engine to calculate the profit of this transaction. Of course, we will combine with other factors to determine whether this transaction is a malicious or not. So if this is a malicious transactions, then we will automatically synthesize a similar transaction, attack transaction, but we will replace the profit addresses in this attack transaction with our own rescue addresses. After that, we broadcast our rescue transactions to the network with a higher gas fee. Because we have a higher gas fee, we use some gas bidding strategies to ensure that our rescue transaction will be ahead of the attack transaction to be confirmed on blockchain. So by doing so, because we are ahead of the hacker transactions, we already move the assets from the vulnerable pool to our own rescue addresses to block the hacks. So this is the basic idea of the attack blocking technique. So there are a couple of different challenges to implement to develop such a system. So the first challenge is that how can we extract the attack logic from the attack contract and attack transactions? Okay. Second is how can we locate and replace the revenue addresses? The revenue addresses are the ones used by the hackers to get profits. How can we locate these addresses inside the smart contract and inside the transactions and to replace them with our own revenue addresses? The third one is how to locate and it's a duplicate. So the third one is that how can we because in some cases the hackers they will use multiple transactions and some auxiliary smart contract to perform the hackers because they need some preconditions, in order to launch a hack. So how can we automatically identify these auxiliary smart contracts and how can we deal with multiple transactions to launch a hack? Okay. So to deal with the first challenge, we use some technique called jump instruction freezing the technique. So the basic idea is that because we need the task is need to reconstruct a smart contract with the hacker's logic, right? And how can we do that? So because we already simulated the hacker's transaction, so we have what do we have? We have the trace of the opcode. The trace of the opcode is the executed instructions during hack transactions. So we can just connect this hacker's opcode trace to generate a new hacker smart contract. Okay, this is the basic idea. But it works theoretically, but does not work in practice. Why is that? That's because the hacker's transaction could be very complicated. If you just connect the opcode trace, the reconstructed smart contract, the size of the reconstructed smart contract will exceed the limit of a smart contract. That's because in Ethereum, the size of a smart contract has a limit. You cannot have a very large smart contract. So what can we do that? So we can reuse the basic block of the opcode trace as much as possible. So I will not go through the details here, but the basic idea is that we do not need just to copy the opcode trace. We can reconstruct the jump, reconstruct the loop structure to reuse this basic block. Because we reuse some of the basic block, the size of the reconstructed smart contract will be reduced. So we can reduce it to a limit of to reduce the size of the reconstruct smart contract to be allowed inside the blockchain network. Okay, so this is the details. I will skip that. Okay. The second task is we need to identify the revenue addresses. The revenue addresses is the one that changes positively, and replacing these addresses does not affect attack logic, right? So basically, this is the address the hacker using to connect the profits. So how to identify them? So we take a try and a catch method. We calculate the balance change table during the transaction, saying that the address A, the profit of address A increase, the profit, the balance of address B decrease. So we construct this balance change table, and we will randomly, replace one of the address, and we resimulate these transactions to see whether the change the transaction will cause revert. Okay. So this is one concrete example. So basically, we have the transaction trace. We will construct a cash flow. We perform the cash flow analysis. Then we will construct the balance change table. The table shows the balance change of each table. Each address. Then we will find the address with the positive balance change, and we will replace this address to resimulate the transaction to see what's happening, to see what happened. Okay. So the third task is we need to identify some preconditions, including the auxiliary smart contract and the multiple transactions to launch the hack. So what can we do, to identify all these smart contract? So basically, the auxiliary smart contract are created by the hacker at the runtime using the create and create2 opcode in the EVM virtual machine. So we can locate the create and create2 opcode during the opcode trace, and we will include, because we can find all this opcode. It's easy to locate all these auxiliary smart contract. So for the multiple transactions, that's because the hackers, they can split the attack transaction into multiple ones. And our method is we can retrieve the state dependency between different transactions. The state dependency means that if one transaction changes the state used by another transaction B, then we say the transaction B depends on transaction A. So we will construct this graph at a runtime. So when we find a suspicious transaction, we can query this graph to find all the transactions that the final attack transaction relies on. So by doing so, we can, identify all the precondition transactions by locating their state dependency relationship. Okay. We also have some optimizations because we need to finish this search in very efficiently. So we use some cache, mechanism to improve the performance. Okay. So whether this system work in practice, we basically we have some evaluations. We use some real hacks, and most of the hack transactions we can automatically synthesize the similar attack transaction using this method. And most of the cases, more than 80% of the cases are finished in less than 25 milliseconds. That means because you need, to finish that very quickly. Otherwise, because you also need to broadcast these transactions. So the quicker your system works, the better of the results. So most of them can be finished in less than 25 seconds. It's enough for the Ethereum and even for the BSC, because BSC has 2 or 3 seconds, to do that. And our technique is not only for papers, but we really deploy this system inside BlockSec. And we block hacks and rescued more than $20 million in the past 2 or 3 years for more than 20 different DeFi protocols. So there are some representative ones. For the Paraspace, we rescued for $5 million for them, and for the Settle Finance, we rescued $3.8 million for them. Okay, and from research to product, right? So research is good, but how to develop a commercial product based on that? Okay, so what about the legal issue? Why do we have legal issue? So basically, the way to block the hack transaction is you perform the similar hack with good intention and return the funds to them. But technically, right, you are also hacking a DeFi protocol. So if we want to develop a commercial product, we cannot do that. Okay. And another thing is, what about the competition between our system and other MEV bots? That's because in order to make the block transactions to be committed on blockchain, sometimes you need to bribe the validators, to put your transaction ahead of others. But this will create the competition between our system and other MEV bots. And theoretically, other MEV bots, they can bribe a very large number of the profit to the validators. But for us, we cannot do that because the profit is not, the profit is the loss of the DeFi protocol. So we cannot just bribe using other money, using other people's money to bribe the validator. We cannot do that. So it doesn't work in practice for a commercial product. Okay, so we need to another solution from the perspective of a product. So we develop a system called a BlockSec Phalcon. So the Phalcon is a platform to monitor and block hacks. The basic idea is that instead of using the technique to synthesize a new hacking transactions, we ask the protocols to pre-sign some pausing transaction to circle break the protocol themselves when a hacking transaction is detected, right? So what we only need to do is when our system detects a hacking transactions, we just need to push such information to the protocols. After that, the automatic actions will be triggered to broadcast the pausing transaction of the protocol, to prevent hacks instead of, ourselves performing the front running to do that. Okay, so this works in commercial products. But the challenge is how to reduce false positives. How to reduce the false positives. That's because if your system has too many false positives, then it will pause the protocol because even without a hack transaction, then it will hurt the usability of the protocol, right? So your system need to have a very, very, very low false positives in commercial product. And how to reduce the false negatives? Okay, so we develop some, optimizations combining with other techniques to make it really effective in the product. Okay, and after developing this product, and we think a little bit further. So can we do these things in the sequencer with the development of the L2 blockchains? Okay, the sequencer is the component inside the L2 chains, which is responsible, to pack the transactions, to put the transaction on the L2 chains. So if we can put all this detection engine or the security capability inside the sequencers, then the L2 chains can protect the DeFi protocol running inside these L2 chains. Okay, so but still we have the challenges: attack detection accuracy, the overhead, the latency, the throughput. You do not want to hurt the throughput of L2 chains. You do not want to cause too much network latencies to the transactions, and also there is some L1 to L2 transactions. So the hackers, they do not necessary to go through the sequencer to send a transaction. They can directly, go through L1 to L2 because the design mechanisms, such transactions cannot be removed by the sequencer. So how to deal with such transactions? This all the practical challenges when you develop a commercial product. Okay. And we were working with the Manta network. So Manta network is using our architecture called the STOP, the Sequencer Threat Overwatch program. So the basic idea is that we hook our capability of the attack detection into their sequencer. And when there is a suspicious attack transactions, then we do not remove the transaction, but we will, put the transaction into an isolated area for further inspections. So it's something like the vetting process of the application market store like a Google Play or the App Store, right? They venture process. So the L2 chains, they can venture the transactions. Okay. So at last, I will spend a little bit to introduce the BlockSec. So BlockSec is a secured company we founded in 2021, and we were backed up by some top investors and customers. So we are full stack security providers. So we provide a pre-launch security, the smart contract auditing. We do that. But besides the pre-launch security, we also have the products for the post-launch security, the Phalcon. The Phalcon is the attack monitoring and blocking platform. And we have MetaSleuth. So MetaSleuth is a community version of the Chainalysis. It can help the institution to do the crypto tracing and investigation. Like if you are a law enforcement, you want to, track the criminals of the cryptocurrency, then you can use our system to do that. And our system can have also have the compliance APIs for the compliant uses, and to help some institution to perform the compliance check. Okay. Yeah, that's all for today's talk. Thanks very much.
Thank you, Professor Zhou, for your insights.